Good afternoon, everyone. So we'll begin this webinar. Okay, so just show my screen. So just to introduce myself, my name's Amit Patel. I work for a company called Intrinsic. A little bit what I do here at Intrinsic. So I'm one of the trainers and one of the application engineers. So get involved with support, with training, training CATIA, and various other different softwares as well that we support and sell. Again, CATIA V5 sheet metal, that's something that I also train in as well. So welcome to his webinar series with Intrinsic. In this one in particular is CATIA V5 sheet metal hints and tips. Again, what I'll be showing here is just things I've picked up along the way. During my training, I get various questions. During my support, I face various different challenges. So I'll be sharing my experience and giving you a few hints and tips of how to work with sheet metal parts in CATIA V5 more smoothly, and also why certain things don't work and how they work, etc. So before we get into it, let's talk about who we are as Intrinsic. So Intrinsic was established in 1998 as an engineering consultancy using Dassault System products. So what we do, we were consulting as engineers and we were just using Dassault System products like CATIA. We then developed into a PLM consultancy operating alongside the engineering business. And at the moment we are UK's largest and best resourced Dassault Systems business partner. Now, as far as I believe to date, we're actually Northern Europe's largest, the Dassault Systems largest business partner. So in Northern Europe, we're #1, not just in the UK, but within Northern Europe region. The PLM business itself employs about 64 people, so 64 employees, and has a turnover of roughly about 12 million annually. The engineering consultancy side, however, is a bit larger, employs around 85 people, and has a turnover of roughly about 20 million annually. We have 5 offices around the world, so 4 offices in the UK and 1 office in South Africa, so that's in Johannesburg. So what do we do as a PLM's partner? We sell software and we also support it. So what softwares do we sell? We sell things like 3D experience platforms, so a single unified environment for all areas of a business. It basically includes your CAD, your BOM management, workflow, multi-site, Simulia. It's a new product that Dassault have released in recent years, and it basically contains anything and everything that you'd need to do within a company. So it contains the entire workflow. We also sell and support CATIA, so CAD tool, which you're all aware of. Novia, so a data management tool, so it's CAD, BOMs, workflow, multi-site, etc. Delmir, so it's a manufacturing environment. Simulia, it's a simulation environment, so things like FE analysis, etc. Optimization, fatigue analysis, that all comes under Simulia. Exalead, so search-based optimization. Transcat, so industry standard PDQ and PLM management software. IMS Post, so machining post-processing solutions, and RAMSYS, so ergonomic studies. So that's like you can build humans and make sure that they're not going to go, they can reach things, etc., etc. Quite interesting stuff. As a consultancy, we implement and project manage projects. So if a customer came to us and needed a piece of software implementing, we don't just sell it to them, we can get them the hardware, implement the software on the hardware, and then basically send it to them or set it up for them on site and have everything up and running for them. So all they need to do is just get on with using the software. So we also do software development as well. So a majority of our customers do require some enhancements or some customizations. So we do in-house software development as well. So we have a team of programmers that develop macros, etc. for CATIA. So once we've implemented our software, we then provide support. So we can do training and help desk. If someone's fairly new to a new bit of software that we've sold them, or if they've got new additional users, we can train them as well. And after giving training or without training, we then provide help desk services. So if someone had an issue, they can contact our support line, just send an email at support@intrinsic.com, and one of our technicians will be with them as soon as possible. Now, as engineering services, we operate as a design consultancy, so we can take a concept model all the way through to detailed design. Someone could basically come to us, have a meeting, discuss what they're after, and then we'll go away and basically create that component, keeping in touch with the customer as they please, and we could take it all the way through to the manufacturing stage. So we'll source materials and process selection or aid with that process. We also do prototype supply and component testing as well, so we can arrange all that, do that in-house if required, and build our own jigs, etc. So in the cost-cutting environment that we all live in at the moment, we can all do structural analysis. So we can do component or assembly analysis, linear, non-linear, thermal, dynamic, any analysis you name it. We can do optimizations, etc., etc. And our expertise, so we have press tool design, styling, patent design and research, casting and mold tool design, jigs and fixtures and vehicle installations. Now, it doesn't mean that everyone at Intrinsic knows about all of these expertise. We may have like a couple of people which will be an expert in one of these fields. So all together as a team, we know it all, or at least we're going to learn. So let's get back into this webinar, which is about CATIA V5 sheet metal design. So essentially there are 4 workbenches: there's sheet metal design, generative sheet metal design, sheet metal production, and aerospace sheet metal design. Now, which one do you need? That's the big million-dollar question. So you'd assume you'd need sheet metal design, nice and simple, but that's primarily for any models that you want to modify that have been created in V5, R14 or prior to that. So even if you have V4 sheet metal parts, you would use the sheet metal design workbench. So it's not to be used to create new sheet metal parts. Again, if you do go to use it, there's no way you can make a mistake. CATIA just won't let you create anything new. Generative sheet metal design, that's the one that we're always going to be using. So if anyone's used sheet metal design in CATIA, that's the workbench that you're probably most familiar with. So it's a dedicated workbench for feature-based sheet metal modeling. It has 2 levels of functionality. It depends on the license, so SM1, SMD. Difference between the two is SM1 gives you lower functionality than the SMD. Now, it doesn't mean it's not a capable license, the SM1. All it will be maybe 2 or 3 tools which won't be available to you. Unfortunately, on top of my head, I don't know what tools they are, but I know one of them would be views management. Okay, it still means you can unfold and fold, you just can't manage the views. Okay, we'll talk about that a little bit more when we come on to views. Okay. Sheet metal production, so that's a workbench for manufacturability checks of sheet metal parts. So the way I see it is a validation workbench. So if you have bends in your model, for example, again, we'll explore all the tools in the sheet metal production workbench. But if you had bends, you may want to make sure all bends comply with a 4mm rad, or you may want to make sure if you unfold the part, it doesn't overlap, etc., etc. And it's only available with an SH1 license. So if you're using sheet metal design currently, you may not see the sheet metal production. Now, aerospace sheet metal design, only a minority has access to that. It's a P3 configuration, so requires an SL3 license. And it's an additional workbench for creating more complex sheet metal parts. Now, it doesn't mean it's superior to generative sheet metal design workbench. It just gives you additional tools. So things like you can now, rather than create a planar primary wall, you can start creating primary walls which have double curvatures. So they're known as webs. We can also quickly create a joggle, and we can also create a very nice flange using surfaces and curves, etc. We'll explore that in a little bit more detail as we go along. Now, the terminology, so CATIA V5 uses certain terminologies to describe sheet metal parts and features. So down the left on this slide, we can see that this is a part which has various sheet metal operations performed in order to get to this final shape. So we started off with a wall. Because it's the first wall that we've created, we call that our primary wall. So a primary wall would be something that was first generated from a sketch and then bends, flanges, etc. created off it. So then we've got some bends from flat. So because I know a little bit about, well, so a bit more than that, hopefully, about the generative sheet metal design workbench, these 4 describes the bends towards the bottom right corner on the component. Then we have a flange, a hem, circular cutouts, and we start dressing it up with chamfers, corners, flanged holes, and stiffening ribs, etc. Okay, and all of these features, press the unfold button. From a click of a button, it will fold and unfold. So what is the current workflow that we need to go through when we create a sheet metal part? So what you do, you create a new part in CATIA, just like you would normally do if you were to create a solid object. And then you'd switch to the generative sheet metal workbench, so generative sheet metal design workbench. Now, all the icons in there will now be grayed out. That's because we need to create sheet metal parameters. So we need to select the sheet metal parameters in the tree, define all the values corresponding to what we're trying to do, and then all the icons will come to life. So we can now create our first wall from a sketch profile, create secondary walls and bends, and then go on to create sheet metal features, cutouts, holes, flanges, and stamps. And then finally, what you do, you'd create a drawing or DXF patterns, etc., etc. Okay, so fairly simple process. There's not really much to it. Now, setting up parameters itself, we have to select the setting parameters icon. We get a dialog box to define the sheet metal parameters. So we define the thickness of the sheet, default bend rads. Again, note it says default. So we can have alternative bend rads throughout our sheet metal component if we want. And then once we press OK, it's then stored in the tree just above the body. So we can easily go back and modify that at any stage. So if I decided that the thickness from 2 needed to be 2.5, just double click on it in the tree and I can change that to 2.5 and it will update my model. Also throughout the other tabs, we have bend extremities. So again, these are just defaults. We define the bend extremities and just fill out the dialog box. Again, we can change them later on as well. So rather than just keep flipping through slides, let's get straight into CATIA and have a look at all these features. So I've just got 2 CATIAs open just in case. Let's create a new part. So if I go into the generative sheet metal design workbench, because I haven't got anything new created, it goes straight into it. Now, you can see all my icons are grayed out. CATIA also has this habit of hiding components, so I just like to drag them all out so they're not, so I can find them when I need them. Okay, so there we go. It's just like picking a bunny out of a hat. It just keeps going. Okay, so this is my sheet metal parameters. Create a parameter. We'll talk about these sheet metal standards towards the end. I'm going to have a 2 mil thick sheet with 4 mil bend rads. Again, default bend extremities. I'm going to say it's going to have round relief. Or I can pick the type from the list, so it gives me a visual indication of what they are. And depending on which one I choose, it lets me fill out the boxes next to it, so the parameters. Now, there's another tab here called Bend Allowance, so we'll come on to that in a second. But if I press OK, it's now stored in the tree, and all my icons have come to life. So, what is this Bend Allowance? It's basically the K factor. What is the K factor? It's basically the position of the neutral fiber. What does all that mean? It's basically derived from the bend allowance of the unfolded bend length, inner bend rad, material thickness, and inner bend angle in rads. So essentially, if I had a K factor of 0.5 and had a sheet thickness of 2 mil, that would mean that the neutral fiber, which is determined from where the K factor is, would be at the mid-plane of that sheet. So it will be at 1 mil from the top and bottom surfaces. So in this case, don't forget, if we have a bend, we've got if there's an inside bend, it's under compression, and then the outside bend is in tension. Okay? So basically, the neutral fiber represents the boundary between these 2 regions, and the position of a neutral fiber as a ratio of the material thickness is referred to as a K factor. Now, You can see in this example that CATIA is grayed out. I can't change it. That is a misconception. So the user does actually have control over what they want to do with that K factor. If I just go back to my part and modify the sheet metal parameter, go to the bend allowance, if I press FX, you can see the relationship which has been created in order to determine that K factor. Now, I can't remember which ISO standard it is, but this formulation is an ISO standard. Again, I'll show you a bit more information of where that is held in the help documentation later on. Or if you just Google sheet metal bend allowance or K factor, it will show you what ISO standard it's referring to. So it's got a fair bit of calculation behind it. But if you want to change your own K factor, this is just a formulation. Just right click on the box, deactivate formula. Now, why did I deactivate and not delete a formula? It's another hint and tip. It's because I can easily go back and activate it. The reason I didn't delete it, if I deleted it, there's no way, unless I'm fairly confident with what the formula is, easily go back to the formula. I'll have to work all this out again and derive it myself. So let's just leave that for CATIA to determine. Now, view modes. So there's 3 ways of managing views. You've got views management. So again, these are all icons. Again, you can access view management by right-clicking on the body, part body object, and views. From a click of a button, you can fold and unfold. And then you've also got the multi-viewer. So what I like to do generally, I don't like to visualize things. You think you can visualize something, but your brain always doesn't like to do too much. So if you visually have both views that are folded and unfolded views on the screen, it's easier to visualize what's going on. And it can help and prevent any problems of any like overlaps, etc., etc. Now, let's have a look at a part. So I've got some demo models already saved. Let's open that. Now, views management, access in 2 places. You've got it here. And you can just right click on the body, go to object, views. It gives you views management. We'll come on to that again in a minute. Now this is my folded view. I'll click a button, unfolds, click it again, folds, unfolds, folds, unfolds. Okay, so it's nice and easy. Now if I go to my views management, deactivate flat view, okay, it won't let me go to flat view because it's deactivated. Now if I set my flat view as current, it just unfolds current. Okay, so it's just another way of unfolding and unfolding. To be honest, I don't particularly use it. Multi-viewer, very useful. So what it's actually done is, if I just close this part I've created, the blank one, it's created 2 tabs. Now if I go to tile horizontally or tile vertically, it puts folded and unfolded views side by side. And now it doesn't mean I have to work in one view. I just click in the window I want to work in, and then I can choose a sheet metal feature I want to add to that view. And it will update into the other view as well. So it depends which one you're more comfortable in working in. Just click in that window. So I'm not going to go over all the tools inside the Generative Sheet Metal Design Workbench. We have a training course on the Generative Sheet Metal Design Workbench over 2 days. To cram that into 1 hour, it will be quite a busy webinar. So I'm just going to cover what I think is useful to know and just some hints and tips which I want to express. So I've found things I may have struggled to understand, why things weren't working, etc. I'll show you how they work, and hopefully it will give you more confidence to create sheet metal components. So Canonic Hopper is based on 2 sketches on parallel planes. Keyword 2 sketches. Another keyword, parallel planes. So the planes have to be parallel. So they can't be skewed by 1 degree or anything like that. It has to be parallel. And it's got to contain 2 sketches. So it's got to be 1 and 2. So if you want the same sketch, you'd have to duplicate it on the parallel plane. Another key thing to note as well is both sketches must contain similar geometry and be tangent continuous. So if you have something like a base sketch which is, let's say, a rectangular section, four-sided shape, and then on the parallel plane you had a triangular section, so a three-sided shape. It's not going to work. Two reasons. One, it's not similar. Two, it's not continuous in tangency. It only works with lines and arcs, equivalent number of, and it must have an equivalent number and sequence of elements. So the rectangular and triangular section, the rectangular section has four sides, triangular three sides. It doesn't have equivalent number of elements. And now, if you have any arcs in there, the arc center points must correspond. It means that they must be coincident. And open profiles can also be used if required. So the sketches doesn't need to be a closed profile. Okay. So let's have a look at that straight into CATIA. Right, we're done with this one, so let's get rid of that. Now, where is my? If I just look for it, Hopper. There we go. So what does this contain? I've got a base sketch, and on a parallel plane, I've got basically the same geometry, it's just scaled smaller. Now, just looking at it, the arc centers don't look like they correspond. Best way to tell, measure. So I get the measuring tool, measure that arc, measure that arc. You can see it's the arc centers in, if I use components on X, that one corresponds, so that one's okay. What about that one? That's 20 mil off, okay? So it's not going to work. I'll show you what error you get a bit later on. So let's just talk about what else we've got. We've got parallel planes, so that sketch is on a plane which is an offset, so it's parallel to that base plane there. And also I've got two extracts. So there's an extract of the two vertices of that sketch. We'll talk about that in a minute. Now let's go on to create a hopper. Change that to Canonic. Okay, it doesn't matter which one you select first. That's the error I wanted to show you a bit later on. So this is basically complaining that the selected hopper sketches are not consistent. Please modify the hopper inputs. I know it's because if I go into my secondary sketch, this arc center isn't concentric with the bottom one. So let's just make it concentric. No, it's concentric. The other one isn't. Could move the sketch. Concentric. There we go. Now, if I go and do that again, let's choose this as the first one. Whoops, change that around. First, second. It's not complaining, so it's happy with the input, but I need to select opening lines. Now, just to show you, if I hide the extracts, I can select the vertices. I have in the past had experience where it doesn't like me to pick the second point as a vertex. And generally, best practice in CATIA is to have extracts. The reason for that is if you delete the geometry, extract falls over. You just update where the what the extract is of. Okay? So it's always a good idea to create an extract rather than just pick topology directly. So let's go do that again. First extract, second. Show me some sort of preview. Press OK. There we go. So now if I fold and unfold, there we go, it's folding and unfolding. Now if I go back into the hopper, again, the first and second point basically defines where the opening line is. The first point's got to be on the first profile, second point on the second profile. Again, I can invert material side, so now it'll thicken inwards, or invert fixed side. So now it should unfold the other way. So next question is, let's delete that hopper. Let's remove that concentricity. So what am I to do if I want to use this profile? Now one of these arcs isn't concentric with the lower one. So if I choose hopper, we saw the error before, it doesn't like it. So I can use Surfacic Hopper, Surfacic Hopper, sorry. Now, what I need to do is create a multi-section surface. I don't have one, so I'll create one on the fly. First profile, second, closing points in the right place. There we go, it works. Again, you can define your unfold position as well. Basic gist of what I'm trying to get across here, if you need to use a profile where the arc centers aren't going to be centered, aren't going to be concentric, just use a Stiffening Hopper and create a multi-section surface. Rolled wall. So if we have an arc, we basically want to make sure that the sketch origin actually passes through the arc, and the origin is also where you plan to unfold that rolled wall. So in this case, it's at the center of this arc profile, so it unfolds about that center point. Okay. Tangent walls. So this is still using the wall tool, but we can actually define a primary wall as a secondary wall. So what we would do here is, if I go to my back to CATIA, let's hide this. Let's have a look at what we've got in this model. Okay, so in the tree we've got a wall. That's my primary wall because it's the first wall in my part. A flange, and any walls that exist after your first wall, I like to think of it as a secondary wall. CATIA likes to think of them as primary walls anyway. The reason it's thinking of it as a primary wall is when I unfold and fold, it doesn't do anything. Now the reason for that is it's because we haven't defined tangency. So I haven't said that size needs to be tangent to the flange face, and this wall needs to be tangent to that face. So technically now it's a secondary wall. Now it will unfold and fold as with the flange. Wall on edge. So in my opinion, if you're going to relimit a wall on edge along a spine, which in this case is this top edge, don't try and do it with offset values. It's always more robust to use surfaces and planes. That's just my opinion, and that's the way I prefer to model. But what we can do is also relimit up to a surface, and it will take the shape of that surface as well. So let's have a look at that, shall we? So if I find my part again, wall on edge. So I'm going to create my wall on edge. On that top edge, just reduce the length of that. Could even change the angle from 10. Now, if I go to extremities, I can pick the left extremity as that surface and the right extremity as that surface. Wait, hold on a minute. That's the extruded surface. So if you have something that's planar or non-continuous in tangency, it will just pick that one face. So if I meant to pick the entire extrusion, I pick it from the tree and it will update to that extrusion. Okay. And again, we can offset from it and it will still hold that shape. And if we update that surface, so let's just update a sketch of that surface. So let's just bring that out a bit. Again, the relimitation updates as well. Okay, so you can always use surfaces and planes for relimiting a wall on edge as well. Don't forget, guys, if you don't have any bits of geometry, you can create it on the fly. So if I was creating a wall, I don't have a sketch, right-click in the profile, no selection box, create a sketch on the fly. Same with a Stiffening Hopper. If you don't have a multi-section surface, no need to go back to the generative shape design workbench to create your surface. Just right-click in the box, create it on the fly. Same with bench from flat, you create a sketch line on the fly. If you're patterning, just right-click in the box, pick options. It will just this contextual menu will just give you more options. Now, part recognition. This is particularly useful, especially when you get parts from a customer or supplier who are using a different CAD software. So generally, you get it in an ISO standard format, a step file. Now, even if that part in a different CAD software was created in sheet metal workbench or something similar, app, whatever you want to call it, it doesn't mean CATIA is going to recognize it. So what you can do is use part recognition tool to turn it into a sheet metal component. So what you can then do is unfold and fold. Primarily useful if you want to add features and then create a drawing and so on. So you can then add sheet metal features to this recognized part. Now let's have a look at that. is one that I've done before. So what have I got here? Defining work object in it. I've just basically got a dumb solid. Let's assume it's a step file which I've imported. If I unfold and fold, it basically does nothing. But then I've gone on to perform a recognition. So that is that icon there, still in the generative sheet metal design workbench, so we're creating parts. I'll just show you what I've done there. And I've just recognized, it can recognize bends, walls, stamps, etc. So I've selected what I'd assume would be the primary wall, so that, or the face of it, so that face there. Now, because it has a different thickness, so let's assume this material thickness is 2 mil. That may be about 4, I can't remember, but let's just assume. It won't know what to do, okay, because it's changing in thickness. So what we can say is keep that face, go to Bends tab, keep that bend. And what it will do, if I just cancel it, it will then reduce the thickness, okay, so it meets the same as the others as well. Okay, and you can see it's recognized everything else, so it will fold and unfold just like a sheet metal component, and then I can go and add flanged holes, etc. as I please. A little hint and tip about bends and swept walls. With bends, it's always a good idea to click the side you want to bend in. So if you want to bend upwards, click the top edge. If you want to bend downwards, click the bottom edge. It doesn't necessarily give you the same result by just reversing the sides. With the swept walls, it doesn't really matter. If you select the top edge, you can just reverse direction. It's the same as clicking the bottom edge. Okay, so I'll just show you that. So let's just create something new quickly. In fact, let's use my demo model, and what I will do is just show you another hint and tip. So this has various different features created on it. You can basically roll back the history by just right-click, defining work object. You can see how this was developed. Again, if you go to Edit, Scan or Defining Work Object, you can see how this was developed as a bend, now with a hole added. A stiffening rib added there, another stiffening rib added there, etc., etc. But let's go back to the beginning. Now, if I create a bend, sorry, a wall on edge, select the top edge, it folds up. Cancel that. Select the bottom edge, it folds down. Now, if I reverse position, it doesn't necessarily give you the same result. So just be aware. I always think if you want to fold up, select the top edge. If you want to fold down, select the bottom edge. Okay. So you could see here, if I fold up, that the back face goes beyond the primary wall. And now it's in line. Okay. If I reverse position, okay, so it goes beyond that end face. But if I had selected flat that bottom edge, again, you just get a slightly different result. Okay. So the gist of it is, if you're going to bend up, select the top edge, bend down, select the bottom edge. Okay. Now, use a flange. This is where you can create your own profile in order to be swept along an edge to create your profile, add thickness to it in order to get your result. What you need to do is make sure there's a coincidence between your sketch and the edge of the primary wall or whatever wall you're coming off of, and you must maintain tangency with the top face. So let's just show you something that's wrong. Let's just create a new part. I'll show you how quick and easy it is. Create a sheet metal parameter. Let's accept the defaults. Create a wall. Don't have a sketch. Create it on the fly on that plane. And I'm a believer in simplicity. Let's just choose a rectangular section. Okay. Now I'm going to create a swept wall. So it's a user flange. Okay, my spine's going to be that. I don't have a profile. Create it on the fly on this plane. So what I need to ensure, let's just normalize that view, is that I maintain. So if I take snap off, coincidence with that top edge. So let's just create a profile. Again, if all these magnetic lines, so the blue dashed lines are getting in the way, hold shift and it'll remove them. It'll stop snapping to things. And there we go, let's choose that. So I need to make sure, choose a constraint, that is coincident to that. And I'll just show tangent C's. I want to ensure that that tangent direction, just an arrow there. Again, if you struggle to pick it, another hint, hold Alt, click near it or on it, and you could select it. So you can see I've got a tangent direction and the spline itself, so I want the tangent direction. And this edge, I want coincidence. And now it's tangent, continuous in tangency. Whoops, it's a bit too close together. So let's just reduce those points. Let's delete. So again, remove point, remove point, remove, 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 remove. There, let's deal with that. And there we go. Okay, so it's a bit too thick for that complex profile. Again, if your sketch wasn't parallel, so let's just go back. Delete the flange. Let's just go back to the sketch. Let's see what that one belongs to. So it's between tangent direction, so let's delete that. Let's just change that tangent direction. So I'll just manipulate the arrow myself. I'll try and do that again. So on that edge, use that sketch. It doesn't. So the profile is not tangent to its support. Modify your selection. CATIA will try and tell you if something's wrong. Now, we'll just talk about this. A lot of questions I have is, what's the difference between a standard cutout and a pocket cutout? So, what is the difference? Now, a standard, so down the left we have the standard cutouts over 2 illustrations, and down the right we have the pocket cutout. We can see the standard cutout always cuts out normal to the surface, or the face in this case. So here's the profile I'm going to cut out from this bend. It does it normal to that face. So that means that this edge will always be perpendicular to that edge and perpendicular to that edge at that point. Okay. Whereas the pocket, it just cuts out in a direction that you specify. So if I say up, it will just cut out in that one direction. Again, a sheet metal standard cutout, if it slightly touches a face, it will propagate the cutout all the way through. Whereas a pocket will just, if you say I want it 2 mil deep, it will only cut out to a depth of 2 millimeters. That's the difference between the two. Circular hole, circular cutout, again, pretty much like a standard sheet metal cutout. So all it will do is create a circular profile and cut out in the direction normal to the surface. So I find this illustration very good to understand what's happening. Also compared to a hole, where a hole defines where one cutout goes, a sheet metal circular cutout, you can have multiple points in the sketch. So I could have about 10 points in the sketch, which defines where I want all my circular cutouts. Pick the sketch, and it'll put them all the circular cutouts at those points. And again, you can update the sketch to add, remove, change positions, etc., etc. Okay, and what else can we do? One thing to note is when you flatten the part, you may get an overlay form of that hole. Now, stiffening ribs. So a stiffening rib needs to be placed. You need to select the outer surface of the bend, and we can select a point on the bend where we want to position the rib, but it's not essential. So let's have a look at that, shall we? Let's have a look at the stiffening rib. If I can find it. I don't think we have something that exists, but we can easily create something anyway. So let's create a new part on that plane. Whoops, I haven't created my parameter, so I need to do that. Click on that. Let's just add a bend. Any old bend will do. Now, a stiffening rib is actually a sheet metal feature. So if I go to the features, stiffening rib, if I try and select the inner bend, it says the selected surface must be the external surface of the body. It must be a cylindrical surface. So it is cylindrical, but it's the internal. So if I select the external, it just positions it wherever I click. Now, we won't go over the dialog box. You just set up the parameters as you please. There we go. But what you can do if you think, oh, I didn't really want it there, is you can see it's created a sketch on the fly. So you can go into the sketch, move this point around, and it'll just update the position. So exit the sketch, and it updates the position of where that goes. Okay. Now, if you wanted to put it somewhere in particular, you could create a point to begin with. So I could say create a point on the external surface at that point there. And I could say stiffening rib at that point on that surface. There we go. And then all I need to do is move that point around, and it will update. Okay, so you could have a parameter or something driving that. Punch. So a punch is very useful as well. Now, I used to get really confused with a punch and die. Hopefully I'll clarify how it all works for you guys. So it isn't very clear, again, as it's a feature. I need to go to user stamp. It's not apparent from the stamp definition box, but if you look at the bottom in CATIA, so specify a surface or a point. Basically, you need to pick where and on what surface do you want to stamp. If I don't have a point, wherever I click, it will generate a point. So I want it on this surface. I'll just click on there, and there we go. Now, what punch am I using? This second body. So the punch exists as a second body. Let's reverse direction, and there we go. I can add another one. So if I show that body, just so you guys can see what I'm doing, punch there, using that. And I could also go on, say, opening face, open up that face. And there we go. On that side, it's cut through. Okay. If I had a point already on the surface, I won't go over it, but just click on the point and then the surface. Now, one thing you guys might have noticed is, what's this position on context? Let's just go and modify, let's just play through this history. Yep, that's the one I want to modify. Let's make it a bit bigger so it includes that body. There we go, that will be fine. Yep, CATIA hasn't fallen over, that's good news. So that's my punch body. So if I go to use a stamp, say I want it here, or just click anywhere on the surface, select the punch. Remember, it will do it wherever you select. And again, I can change the angle of it, change the position by modifying the origin point, etc. But if I do position on context, there we go. The bend rads were too small. It will do it wherever you've positioned it. Okay. So that's what position on context does. It just moves it to where the stamp actually exists. The reason why you may not necessarily have that already active, as you saw in my example, you have one body which contains the punch somewhere else, and you may want to punch in various different locations. Now, another example. We've got a punch and die. Let's show you a hint and tip of how this works. So with a punch and die, you essentially, best way to do it is have a body, a product or an assembly. Let's just show you the final result first. So all I've got is this sheet metal component, which has been punched. I'm just going to activate that punch and let's just go back to the start. There we go. So I've got two parts in my assembly, one which is the sheet metal part itself, there we go, and another part which contains the punch, which is that one there, and the die itself in two separate bodies, so the punch and the die. Okay. What I would then do is use the assembly to position the punch where I like it. So I could change that to, let's say, 60, update, now find my update button. seems okay. I think it's because it's fixed. But let's say I've positioned it to wherever I like. I can then go into this part, multi-select the punch and copy, go into my sheet metal part, paste special. You can paste it as a result with link, etc. Let's hide that part. And then it goes in at the correct position. So now I can just say, use a stamp. Sorry, that's surface stamp. Use a stamp. That warning's just saying I had the wrong body selected, so it's going to put it in the part body. Punch and die, select the punch body. Whoops, before we've done that, I need to select what face I want to punch. So it's that one there. Punch and die. This is the punch. This is the die. Position on context. And there we go. So it will do it wherever the punch and die is. If I didn't do position in context, it will do it wherever I clicked on that face. Okay, so use an assembly to reposition where that punch and die needs to go. Now, aerospace sheet metal design. So what is a web? So a web is like a primary wall, but it lets you create a wall which has double curvatures. Okay, so we can add features to sort of go around in this sense. So let's have a look how that works. So let's create a aerospace sheet metal web. So this is an aerospace sheet metal design workbench. I'm going to create so it's the wrong workbench I'm in, aerospace sheet metal. I'm going to create a web. The support is this surface, and it's generated that. So already I can see how it differs to a wall. It allows me to create a web with curvature. Now let's go back and modify that. I'm going to limit it so it goes up to that surface. Now it's picking a face there, so I'm going to pick the surface from a tree and that surface there, and then that sketch. And now I need to define where we're going to unfold. And you'll get this wireframe preview when it's happy with it, and obviously the preview button. Press OK. There's my web. Okay. And if I unfold and fold, I find the icon. It's just here. It's hiding away. There you go. It unfolds and folds. Now if I hide all the other gibberish, not show it. Hide it. There we go. Okay, so it lets you create something with curvature. And then I can add a Cephalic flange off it, etc. So, coming on to Cephalic flange. Now, what's the benefit of this? I can use surfaces and or as a curve or both in order to define my flange. Okay. So again, it copes with double curvatures as well. So as long as your surface is double curvature, it will just basically flow with that surface. So let's have a look at Cephalic flange. Now, what I can do, again, in the aerospace sheet metal workbench, Cephalic flange, pick the base feature, which is that web. It could be a wall. Now the support is going to be that surface there. That's 100 mm long. There we go. It's a flange which follows that wall. A bit more cleverer than that. I'll just go into no-show and just show this one. That profile actually sits on this surface, and I can actually get my Cephalic flange to take form of that profile. So if I go back and modify it, go to EOP tab and the folded form, set that as a boundary and go to sides and corners and set the sides as none. There we go. It takes the form of that, but still maintaining the shape of that wall. What else can I do? Let me show you something else. So I have hidden away the form I want it to take when it is unfolded. I think that's showing all of it. No, it hasn't. Show and show. There we go. So if I go back and modify this, now I can say OEP, so I'll still use base feature, primary web. Support is the surface. I go to OEP, element for FP, so folded part. Select that, as the boundary elements, and on sides and corners I'm going to say element FP. One side's that side and the other one is going to be this side. It takes the shape of that but still along that surface. So if I unfold, in the unfold it uses that profile to sort of shape it. Okay. And then finally, the other tool in the aerospace sheet metal design is the joggle. Okay. So let's say if I had maybe a sheet metal part I needed to go over, I can quickly do that by creating a joggle on the fly. So let's have a look at that. Let's find my joggle. Again, aerospace sheet metal design workbench. Key thing to note is as well, you can't use the parameters from a generator sheet metal design workbench. It has to be aerospace. The reason for that is it has some other parameters. So you've got the parameters, so sheet thickness, default bend rads, bend allowance, but you've also got parameters for the joggle. Okay, so it won't let you create a joggle unless the correct sheet metal parameters exist. So you can only create the aerospace sheet metal parameters from the aerospace sheet metal design workbench. Now I want to create a joggle which goes over this second body. I can select joggle, support, I want to create it on this flange plane. So where do I want it to begin or end? Up this plane. And I can choose which direction, again invert run out direction. I'm going to say it ends at that plane, which is where that sheet metal part starts. Set the other parameters and there we go. Now it clears it. Unfortunately, you can't then do the reverse on the opposite side, so you can't have it going back down on the other side, unfortunately. Okay, so we're getting close to the end of the webinar, so I'll just talk over the sheet metal production workbench. Okay, so all these workbenches again are found under Start Mechanical Design, but not all grouped together. So you've got sheet metal design, aerospace sheet metal design, sheet metal production, generator sheet metal design here. We're looking at sheet metal production. What can you do with that? So this is a toolbar in particular. You can do something called walls recognition. So I've got a part which contains a pad which was shelled, a few more pads and then pockets. They're not sheet metal features. I've then said walls recognition. And then it recognized all these separate walls as individual walls. Now, it hasn't actually included bend. So even though they're at 90 degrees to one another, they haven't got like a 2mm bend between them. So then you could go on to use bend wizard, and then it will add all these purple surfaces or purple faces as bends. So it will include the bends between them. You can also check for overlaps. So if you unfold the part, you can say overlap check, and it will check where the overlaps are. And it will also create a geometry, so in this case a little square of where the overlap is. You can check bend rads. So in this case we have one bend which is larger than the other bends. So it will check them, and well, not with one another, it will check against the default bend radius that we specify in the sheet metal parameters. Okay, so in this case it's flagging at 1, which is different from the default. And then finally we have check features. So where we had that tangent wall example, where it wouldn't unfold and fold with the flange, it will check and just tell you what features aren't working, so what won't fold and unfold. Okay, so in this case it's flagging the two walls. Now, what else can you do? You can actually use multi-body modeling when you're working with sheet metal design. Let me go and show you how that works. Okay, so multi-body. So here I've got two bodies. I've got a sheet metal parameter, back to the generator sheet metal workbench. First part just contains a wall, and I've added a stamp just so it looks a bit more like a sheet metal feature. The second body creates a wall, it just has a wall. Now we're all probably aware of Boolean operations, so I can right click on the body and add. That's not what we're going to do. From a sheet metal workbench, we're going to use bends, or bend. So the first support, generally first support is the body I want to add to. And then the second support from a second body. Okay, and there we go, it's added the wall, added a bend. And you can see under a cylindrical bend, which is added under the part body now, you can see that body underneath it. Again, you can have as many bodies as you want, but that's how you put two together. So you can use multiple bodies when you're creating sheet metal components. Now finally, the standards file. So if you're working with certain sheet thicknesses, you can set them as standards. It's a good idea because it saves you having to work things out. It saves you other users using non-stocked items, for example. So you create a Excel sheet or a text file, which contains, so let's look at an Excel sheet, following headers, so in column headers, and then you just fill out the rows. Okay. So we won't go through and do all of them, but what we can do, if let's create a new part, easiest way. Now if I select sheet metal parameters, sheet standards file, I'm going to pick this standards file. It then means that all of these are grayed out. But if I select the icon next to them, I can pick which standard I want to use. So let's go with a 1 mil thickness. Create my primary wall. Okay, and it was 1 mil thick. It needs to, I've decided that the thickness isn't adequate. Someone's done an analysis, it's going to fail. But what other sheet sizes do I have in stock? Sheet metal standard. I could use this standard 5. It adds the thickness. It will just update everything. And it's not just for the sheet metal parameters. It also works with sheet metal features as well. So you saw with the stiffening rib example, or in my case, I think I have a flanged hole example. So it's got a flanged hole on that face. Standards file, and it's found it in the same directory. Okay. So again, that's probably too big, and I can pick which standard I want to use. I think all of these are going to be a bit too big to demonstrate. Okay, so you can see it's too big. So how do you know what headers? How do you build these assemblies? Excel spreadsheets or text files. How do I know to use them headers for the flanged hole standard, or these headers for the sheet metal standards? That's all described in editing the sheet metal and tool parameters. So that's found in the help documentation. Again, if you don't have that available, just press F1. So if I go into CATIA parameters, press F1 directly. Let's go to editing the parameters, and there we go. It takes me to the help page of that. So what do you want to look for? If I just go back to the PDF, you want to search for editing the sheet metal and tool parameters, otherwise we can look at it there. Again, if you don't have the help documentation on site, please speak to your CATIA reseller, and they should be able to ship you out a documentation disc which contains the help files. So if I have a look at this, scroll down, it tells me what I can apply standards to, and then below what headers I need to use. Okay, so it's all in the online help documentation. So carrying on with the online help documentation, there's also a nice, if you search for computing the bend allowance, a nice page which shows you how it's all computed, or calculated, my apologies. Okay, so just search on the online help documentation, so computing the bend allowance. Again, easiest way, have the parameters open, press F1 if you have it installed, define the bend allowance, takes you to the help page of that. Okay. So that basically concludes our sheet metal design webinar. So what can you do next? You can actually follow our blog. So if you go to www.intrinsic.com/blog, we, myself included, and various other technicians and engineers that work here, submit weekly blogs. So they're not necessarily about CATIA, it could be about other software we sell, it could be about just best practices for engineering. So if you're trying to design something, one of our design engineers may think, this is useful to know, I keep having this question, and submit a blog. It's about anything and everything. You can learn things from it. All our technical staff even go on there as well. We all learn from it as well. If you're interested in training or just want to have a look at what training we acquire or want to learn more about sheet metal design, you can go to www.intrinsic.com/training. If you want a customized demonstration, or if you have any questions at all, you can go to www.intrinsic.com/contact, or alternatively, you can email our support line at support@intrinsic.com. You can stay informed by following us on Twitter. You can subscribe to our YouTube channel, and you can follow us on LinkedIn. Okay. Now, before we conclude, I just want to show you another hint and tip, one of the most useful ones I find. Now, if you go to our home page, don't forget, guys, if you want to know more about sheet metal, just go to www.intrinsic, if I can even spell it myself, .com. Okay. And then from that web page, what you can do when that eventually loads is, I was having a bit of a wobbly. Is then actually, well, there we go, better late than never. But if you go to search, you could just search sheet metal, for example, press enter or press search, and here we go, it finds things everywhere. And it also, which is a benefit, actually searches our blog as well. So recently I've submitted a blog on generative sheet metal design wall versus aerospace sheet metal design web, okay? And it will find that. So if you have any problems, not even related to sheet metal, just any CATIA questions or want to know more, try search for it on our webpage. Okay, so www.intrinsic.com, search, and just type what you want to look for. Okay. So thank you guys for listening. I hope you enjoyed this webinar on CATIA V5 sheet metal design. And if you have any questions, I'll be more than happy to take them now. But thank you for listening.